Well, good morning, everyone. Welcome to the first press conference of this 228th meeting of the American Astronomical Society here in San Diego, California. I'm Rick Fienberg. I'm the AAS press officer, and I will be moderating the proceedings this morning. We're going to be webcasting the briefing, and I have Michael Zevin from Astrobytes, who the AAS is newly partnering with, helping me by monitoring the webcast. If you're online, please report any problems to Michael via the chat feature. And when it's time, or when you're ready to ask questions, please use the text chat for that as well. A couple of press releases will be going out this morning right after the briefing. Actually, I think there are three. And so I will now introduce the topic and speakers. So the theme of this briefing is exoplanets and brown dwarfs. The field is mature enough now that no AAS meeting goes by without at least one briefing on exoplanets. We have four speakers today. The first will be Carl Melis from the University of California at San Diego. He'll be speaking on the surface of a limestone-rich world. He'll be followed by Avi Shporer from the Jet Propulsion Lab, the first transiting brown dwarf from the Kepler K2 mission. Then Jerome Orosz from San Diego State University will speak on the largest and longest period Kepler transiting circumbinary planet. And finally, we'll wrap up with Sean Mills from the University of Chicago, the only non-local person on the panel. Kepler 108, a mutually inclined giant planet system. So with that, I will turn it over to Carl.
All right, hello everybody. Thank you for coming to this press conference. I'm going to apologize in advance because I'm recovering from a cold, so I'm going to hack and sneeze and sniffle my way through this. If you can bear with me, we'll all make it through together. So I'm going to give you what I consider to be the main points right up front. If you take nothing else away from this little presentation, I hope it is these 3 points. The first of which is that we can use white dwarf stars as a window into the interior structure of massive rocky exoplanets. And we have observed a particular object by this name, SDSS J1043, with the Keck 10-meter telescope and the Hubble Space Telescope, and found that it indeed appears to be including what looks to be the surface layers of a planet-like object. And in particular, this material appears to have a high carbon content. And we've come up with a model that explains this carbon content and all the other elements that we see that are being accreted onto the surface of this white dwarf star using calcium carbonate. We can actually make this object be up to about 9% calcium carbonate by mass. So we'll explain why that's important later. So the background, for those of you who are not familiar with white dwarf stars and how they tell us about planetary systems. So as we all know, planetary systems orbit main sequence stars. We know about a lot of them. We'll hear about some more today from the Kepler satellite. Once that star dies, like our sun will eventually, something's going to happen to the planetary system too. Planetary system will begin to decay, usually through chaotic dynamics, and some rocky material, like planets or asteroids or whatever, will find their way close enough to the white dwarf star that it can actually be ripped apart by the gravitational forces of the white dwarf, literally shredded. And so that's what the first image here is showing. And then that shredded material will go into a disk-like configuration around the white dwarf and eventually accrete onto the white dwarf star, polluting its atmosphere. At that point, you can go with an optical spectrometer or an ultraviolet spectrometer, take some measurements of the white dwarf star in question, and look for the atomic abundances of that rocky material. So this is not new. We've been doing this for over 10 years. And what I'm presenting to you today is a new object that we've been investigating. Again, with this long phone number here, somebody can hopefully come up with a better name for it after this. So what we found first and foremost was that this object appears to be accreting rocky material that is severely deficient in iron. Now, why that's important is because the surface layers of the moon, the surface layers of the Earth, are very depleted in iron because of differentiation, which I'll talk about more in a few seconds. So this compelled me to make a comparison to this object to what we call the silicate moon, which is just the surface layers of the moon, and a model I mocked up of the Earth where I take out its core and I take out the lower mantle and I call it the hollow Earth because I'm clever. And you get actually a very good match to the data. And so here's what's been plotted on this is the number abundance of different elements relative to magnesium normalized to the silicate moon. So if this thing was accreting the silicate moon, you'd get everything on this dotted line. It would just all be one. The hollow Earth model, you can see these triangle or diamond data points. They sort of bounce around, but they're more or less near the line. And the actual observations of the white dwarf star in question indeed also follow very close to this line, and more so actually the hollow Earth model with a few discrepancies, clearly aluminum being in the wrong direction there, very depleted in the white dwarf but not in the Earth. And then there's carbon, which we'll come back to. So this model actually looks like a reasonable fit to the data, and it makes me feel like we're looking at the surface layers of a differentiated, massive rocky body, maybe a planet like the Earth. So differentiation, I keep saying this word, what does it mean? Differentiation is basically when you melt stuff, the heavier things go to the middle, and the lighter things kind of sit on the top. So that's why the center of the Earth is mostly iron and nickel, and you get a lot of silicon and magnesium in the outer layers. So after finding an object like this, I was compelled to go look through the literature and ask myself, how many other objects can we look at that have signatures of being from different parts of a planet, a massive planet that's been differentiated? And so I got these two plots here, which I'll explain. On this one, we're plotting the iron abundance ratio relative to silicon versus magnesium. And so this is basically looking at the major constituents of rocky material, iron, silicon, magnesium, and oxygen. I just get rid of oxygen because it's in everything, no matter what you do. And so what we find here is that you can have some objects that are incredibly enhanced in iron, like this object way out here. And interestingly, it's not just magic. It actually is mostly iron. In fact, that particular object is about 80% iron by mass. So if you don't believe that that's the core of a differentiated planet, then I'd like to hear your counter ideas. Then we have on the opposite side of that things that are extremely deficient in iron. And so the object that I'm presenting today is this data point with the big error bars, but basically one of the lowest iron content objects that we have observed polluting the atmosphere of a white dwarf star. And that's verified over here by looking actually at the percent amount of iron in the accreted material. And it's very low, again indicating that iron is severely depleted in this object, and it looks like this is an object that has been differentiated, and we're seeing the surface layers instead of either the full body or the core of it. So returning back to the carbon and some of the oxygen, we wanted to try and understand where this carbon comes from. So there's a bunch of text here, just ignore it. The big question is, where's the carbon coming from? This is weird, right? The Earth, the moon, everything in the interplanetary system for our solar system is extremely carbon deficient. We call it a carbon desert. But this thing's about 1% carbon by mass. That's very unusual. So we want to understand, where is this carbon coming from? Now, usually when you have carbon in these sorts of planetary mass objects, it's either locked up in an ice as CO2, or maybe as a CO2 atmosphere. The problem with CO2 in that volatile form, either being an ice on the surface or being in a gaseous atmosphere, is that during the asymptotic giant phase of stellar evolution, all of that CO2 is going to be removed. So you need to lock it up somehow in the actual surface of the planet to keep it, so it actually can accrete onto the white dwarf star. So we came up with a toy model to accomplish just that, and we do that by taking all the calcium and carbon and put it into calcium oxide and CO2 and making calcium carbonate. Calcium carbonate is a solid mineral, and so if I have a surface of a world that's covered in calcium carbonate in solid form, it can survive the stellar evolution. It can make it to the white dwarf star to be accreted. So in particular, we did a few mock trials and just to see how much calcium carbonate can we make this thing actually have. And we can actually push it up to 9%. So almost a tenth of this planet's surface would be calcium carbonate by mass. Now, okay, this isn't proof that this is calcium carbonate we're seeing. All we see are the atoms, right? So we need some other way to verify that this is a correct interpretation, and that can actually come through the James Webb Space Telescope. It'll be able to take mid-infrared spectroscopy of the dust that surrounds the star, which you can sort of see up here. We tried to fit it into our little artist impression going on there. There is a disk of material around this white dwarf. It's a material that is being accreted onto the surface of the white dwarf. If we can see calcium carbonate in that dust, then we have to know it's there. It probably won't be 9%. It'll probably be less than that, but yeah, that's still a pretty decent amount. So what does that mean? Why am I making a big deal about calcium carbonate? For those of you who haven't made the connection yet, calcium carbonate is the dominant mineral in limestone, and limestone has connections to marine organisms on Earth. Marine organisms produce calcium carbonate, making shells. They die, the shells sink to the bottom of the ocean, get compressed, and eventually end up as limestone rock. And that makes this beautiful karst landscape that we're trying to illustrate here. That's actually a picture from Earth, don't tell anybody. So that's the gist of it. Just to review, take us back to the beginning, summarize. I think really the big result that we've got here is that we can actually look at the internal structure of massive differentiated rocky bodies through watching them accrete onto white dwarf stars. Now we have to be lucky, and the white dwarf has to be accreting some certain layer, but it looks so far that it's good. We've got some objects that look very core-like. We've got several objects now that look like they're very crust-like. So this looks like it's a really solid means to actually investigate the internal structure of these objects. So for this particular object, SDSS J1043 plus 0855, we performed Keck and Hubble Space Telescope's observations that make it look like it is indeed the crust, and it has a high content of carbon, which we like to model using calcium carbonate. And that's it. Thank you.
So hello everyone. I'm here on behalf of an international team of astronomers. We have gathered data from space and from ground-based telescopes across 5 continents. And we have discovered the first transiting brown dwarf from the K2 mission. Now, to convey to you why this is such an important discovery, I will start from the observation that most of what you can see in the night sky with your naked eye are stars. But we know that those stars are not alone. Stars are very social creatures. They like to live not alone. So we know that most stars have something orbiting them. And for example, we know that many, if not most, of the stars have planets orbiting them. And if we put those planets on this mass scale, we know that more massive planets are less likely to exist, and less massive planets are much more likely to exist. If we move on this mass scale, eventually we reach the mass of stars, meaning the system will be a system of 2 stars, what we call a binary star or a double stars, 2 stars orbiting each other. And this is how it will look like on this very, very simplistic diagram. So we see there is a gap in the middle. There is a gap in the mass range of objects orbiting stars. The objects in that gap are known as brown dwarfs, and we nicknamed this gap the brown dwarf desert. It is simply very rare to find an object in that mass range orbiting a regular star. And that mass range is roughly from 13 to 80 Jupiter mass, but please do not be very much attached to these specific numbers, because that's a matter of a lot of debate and discussion in the astronomical community. Now, we have measured an object orbiting a regular star with a mass exactly inside that brown dwarf desert. We have its mass, but we also have its radius, its size, because it was observed by the K2 mission. The amount of decrease in flux as the brown dwarf moves in front of its host star tells us the radius of the brown dwarf. So here are the 2 transit light curves, 2 distinct, separate transit events that were recorded by the K2 NASA space mission. We saw that. We went for our ground-based telescopes, and we got 2 more, or 1.5 more transit events recorded from the ground. We used 1-meter telescope from the ground, so you can see, you can compare the quality of data using a 1-meter telescope in space, which is K2 on the left, and a 1-meter telescope on the ground, which is on the right. For the ground-based observation, we use the LCOGT network. If you're not familiar with it, I highly recommend that you look it up, lcogt.net. It's a fully autonomous robotic network of 1-meter telescopes all over this planet. And the two telescopes that recorded these two transit light curves, their location is marked in red in this Earth map, and they are located in in Africa and South America. Now, so we have the transit light curve. So the second part of the discovery, we need to monitor the velocity variation of the host star as it moves around or as it orbits the common center of mass of this two-body system. And we have done that through our good friends in Geneva Observatory, and they have used spectrograph in France and Chile. So we have the light curve, or the transit light curves. We have the radial velocity curve that completes the discovery. We have the radius and the mass. This object has the unique name of EPIC 2017-02477b. The lowercase b signifies the companion, the brown dwarf in this case. The system is a 41-day orbital period. The brown dwarf is just slightly smaller than the size of Jupiter, and it has 67 times Jupiter's mass. So it is right inside that brown dwarf mass range. I'm also showing here the error bar just to show you this is a very precise mass measurement, and the paper has been submitted for publication, and it is led by Daniel Baylis from the Geneva Observatory. Now, to show you just, to give you some perspective, we know today of hundreds, if not thousands, of transiting planets. And on the other hand, we know of thousands, if not more, eclipsing stellar binaries. Compared to those large numbers, we know only of 11 transiting brown dwarfs. This will be number 12. So in analogy to nature, where more rare elements or rare substances have a higher financial value, and inspired by the fact that we are in California, we can say by the discovery of a transiting brown dwarf, we have struck gold. Now, I'll show you just one scientific aspect of this discovery. Here are the mass on the y-axis versus the orbital period. On the x-axis, orbital period is shown in logarithmic scale. First, you can see that the new object marked in red is the second longest period transiting brown dwarf. You can also see there seems to be a separation or a bimodality in the mass distribution of brown dwarfs. We have the high mass brown dwarfs between or above roughly 60 Jupiter mass. They might be the low mass tail of stellar formation processes, meaning they form like stars. And then we have the low mass brown dwarfs from roughly 20 to 40 Jupiter mass. And they might be the most massive objects that can form like planets in a protoplanetary disk. This is still low number statistics, and hopefully we will have more objects that we can study better this bimodality. So I will summarize. This is a discovery of a transiting brown dwarf. It is only the 12th such object to be discovered, so we have struck gold. It is the first such discovery from the K2 mission. It has a very high density, the highest among brown dwarfs. It even has higher density than any known planet or any known regular star. And this is all to be expected. Just to give you some feeling of how high the density is, it is 10 times more dense than gold, which is one of the densest materials we know of. It has a relatively low radius, again, according to theoretical expectations, or well-matching theoretical expectations. And also, low radius goes hand in hand in a high density. And it is the second longest period transiting brown dwarf that we have ever discovered. Thank you, and I'll be happy to take questions later.
So good morning. Today I will tell you about the longest period and largest circumbinary planet discovered in the Kepler data. So as we've just heard, most stars like to have companions, and so binary star systems are quite common. Something like half or a little bit greater stars that you see at night with your naked eye would be in binary systems. Now, what we call a circumbinary planet is a planet that orbits two stars, so it orbits outside a binary system as opposed to a single star like the Earth. And so think of Tatooine, like in Star Wars, where Luke Skywalker is seeing two suns. Now, the Kepler mission has been very successful in discovering exoplanets, and in particular, it's established a new and growing class of exoplanets, the transiting circumbinary systems. And so there are about a dozen members confirmed to date. Now, the one I'm telling you about today, Kepler 1647b, is the most recent addition. It has the largest mass of the planet. The radius is the biggest, and its orbital period is by far the longest in this group. The lead author is Veselin Kostov, and this paper will appear in the Astrophysical Journal in less than a month. So what we actually observe with the Kepler telescope, it just records brightness versus time. And so on the top, we see a graph of the brightness versus time in days, and so we have like 25 chunk days in the graph. Now, this particular binary star system has its orbit oriented edge on, as seen from the Earth, and so the stars periodically eclipse each other. And so you see in the upper left the dips caused by the eclipses, the stellar eclipses, when one star goes in front of the other. And so during primary eclipse, you lose about 20% of the light, and then during the secondary eclipse, you lose about 15%. Now, if you have really sharp eyes, you can see tiny, tiny, tiny dips there in the light curve, and we've zoomed in here on the bottom. And so the event on the left, you see a transit of the planet across one of the stars, and so that causes a very, very tiny dip in brightness, less than 1%, so about 0.2%. Now, this particular dip was first spotted in 2011, back in the early days of the Kepler mission. And for the longest time, we were looking for the second dip, because you need several dips to establish a periodicity. And finally, 3 years later, we finally saw the second set of dips. And so around day, in these units, 1,109, we saw the second dip, as you see in the lower right. And so very similar in depth to the first dip, but a little bit longer in duration. So what is actually happening is the view from the Earth, the binary system's viewed edge on, and so as we go in that little cartoon from day 0 to day 5, at day 0 we see all three bodies basically in the same place, and so the planet is in front, the red star is in the middle, and then the brighter star is in the back. And so that's during the primary eclipse, and during that primary eclipse you also see the transit, and so in the upper left you see what it looks like in the data. So you see a big dip from the stellar eclipse and a little bit of a notch from the planet. Now, about 4.5 days later, so everything's moving, the stars are orbiting and the planet's also orbiting. About 4.5 days later, the planet crosses in front of the secondary star, which is a little bit dimmer. And so it makes a separate dip in the light curve. This is what we see in the lower right. Now, in the upper right, we have an artist's impression of what you would see on the sky if you could magnify it a great deal. And so we see the planets in front, makes that little shadow, the secondary stars in between, and then the brighter primary stars in the back. So this particular circumbinary planet is by far the most massive out of the set that we know of. Its mass and radius are similar to that of Jupiter. The next nearest competitor is less than the mass in radius, the mass and radius of Saturn, or even smaller. And so it sort of wins that contest by a factor of 2 or more. Now, in the lower right, we see schematic diagrams of the orbits, and its orbit is by far the largest orbit in terms of the size and the orbital period. So the orbital period is about 3 years, and the size of the orbit is a little bit more than twice the orbit of the Earth, which is kind of shown in blue. So notice most of those orbits of the previous known systems are very, very close to the binary star system. This particular case, the planet is much, much further out, which is unusual for these class of objects. Now, this particular planet happens to be in the what we call the habitable zone of its parent binary. And so think of the habitable zone as the place in the solar system or around your star where it's not too hot or not too cold to have liquid water. So if you're really close to the sun, like on Mercury, it's too hot to have liquid water. If you're way far out, like Jupiter, it's freezing cold. And so the Earth is sort of in the middle where we can have liquid water on the surface. Now, Kepler 1647b has what we call an insolation pretty close to that of the Earth, about 75%. And so that planet itself is probably a gas giant, but if it had a moon with a solid surface, liquid water could exist on that solid surface based on the expected conditions. Now, because this planet is the same mass and the same size as Jupiter, we expect it to have similar composition. What's different is it's much closer to its parent stars, and so it's much warmer. And so we speculate that this planet would look bluer if you could, see it up close. It look much bluer than Jupiter. Now, sort of the key points here, it's this system Kepler 1647b is by far the most massive and largest of the new circumbinary planets, similar to that of Jupiter. It's got a very, very long period for this class, and so it kind of breaks this pattern that we've been seeing where all the previous systems were very, very close to their parent binaries. In fact, they're so close that their orbits are nearly unstable, but not quite, and so they're sort of near the limit of where they would be unstable because of the gravitational perturbations. And so this breaks that pattern where we have a far out, a system further out. And so this is an important system theoretically because it represents a population of much longer period, much more massive circumbinary planets that we think should exist based on theories of formation, but so far have not been seen. Larger planets are very much easier to spot with the transit method, which what Kepler uses, and so the fact that the previous circumbinary planets were much smaller than Jupiter is actually telling you something. And so it seems like the smaller circumbinary planets are much more common than the larger ones, and so this is kind of the first case of that larger class, which should exist, but so far have not been seen. And so as we get larger and larger samples of these objects, we get better statistics, and it helps inform the theories of planet formation. And so the key question is, does planet formation around binary star systems act or behave in the same way that planet formation around single star systems do? There are common features and there are differences, and so the way to understand this is to get large samples of each class and to see similarities and differences in those things. And so I'll leave you with some links and contact pages, and so we have artwork at these links, and then there's my contact information, and I'll be happy to take questions later. Thank you.
Hi, I'm Sean Mills from the University of Chicago, and I'm going to be talking about Kepler 108, which is a two-planet Kepler system identified previously via the transiting planet technique, which we've just heard about, using the Kepler spacecraft, and then reanalyzed by myself and Dan Fabrici, also at University of Chicago. So to understand what this planet system makes it interesting, the fact that it's mutually, yes. This system is unique because it's a mutually inclined system of planets. And mutual inclination means the planetary orbits are not in the same plane. So to give a little background, we expect when planets form that their orbits are nearly in the same plane, have a flat orientation. That's because they form in a gas and dust disk which surrounds a star in the star's early life. Gravity causes this disk to collapse into a flat surface, a plane, and much like the solar system, the planets that result from it are very flat. Most exoplanet systems observed today are also in a flat configuration consistent with their formation in a disk. However, if planets are not in a flat orientation, if they're not coplanar, then their orbits will wobble around in a circle. This is known as precession, and it's the same effect as you get if you spin a top on a table, and the face of the top and the handle of the top will spin in a circle due to the pull of Earth's gravity. If you have a multiple planet system, then each planet will pull on the other one just like the Earth pulls on a top and spin the orientation of the orbits around. That means the planets do not successively transit in exactly the same way each time. Instead, sometimes the planets are not transiting, and when they are transiting, the planets are moving around on the face of the star, as can be seen in the upper right-hand corner. Kepler 108 is a candidate system which could exhibit such behavior because it has 2 planets which are both pretty massive. I've drawn them here as Saturn because they're approximately Saturn mass, although the rings are artistic license. We can't actually see what these planets look like. The periods of these planets are about 50 and 190 days, so their year is shorter than the Earth's, and they're a bit warmer than Earth is. This system also has a long period binary star with roughly a 4,000-year orbit, so it's pretty far away from the system and doesn't directly affect the system over the Kepler observing window, over the 5 years of data that we have so far. But if we look at the transits of the planets, the transit's exact shape and size change as a function of time. I have a plot here of successive transits of the same planet on the same star. Normally, if the planets were in a flat orientation, you'd expect every transit to look virtually identical. However, each transit here, as signified by a different color, when plotted on the same scale, changes in width and depth a small amount. This indicates that the planets and stars are not changing in size, but in fact that the planet is moving up and down the face of the star, just as indicated in this diagram. So the orientations of the planets, as we view them from the Earth, look something like this. These are clearly not coplanar planets like the solar system and almost all other exoplanet systems found so far. These planets are about 30 degrees inclined to each other on sort of crossing orbits like this. This is significant because, as I said, we expect planets to form in nearly coplanar formation due to the presence of a disk. However, when the disk dissipates, if there are many planets, more than the 2 we observed today, possibly 3 or more planets, and they start interacting, it's possible these giant planets, these gas giants like Jupiter and Saturn, will collide and scatter off of each other. So the most likely formation mechanism for a planetary system like this is the addition of additional planets which are no longer visible, which scattered off one of these planets and sent it into an orbit that's askew from where it formed in. The planet that scattered the planets that we observe probably either got ejected from the system, sent into the star and eaten up, or it's also got scattered into a wide orbit that we can no longer view, and so we just cannot see it around the star currently. That's not the only explanation for the system, though. Particularly the distant binary star that I mentioned is also in the system, may be perturbing the outermost planet and twisting its orbit so that it is no longer coplanar. But in conclusion, this system is interesting and important because it allows us to look back billions of years in this planet system's history and see that perhaps there was a scattering event, a violent history of giant planets bumping each other off of their initial orbits and into these mutually inclined orientations. Thank you.
Thank you very much for very interesting presentations. There's always an awkwardness to the applause in press conferences. Generally, reporters don't applaud, because it seems unseemly somehow. But the press conferences are open, so regular attendees show up and they start to clap. So the fact that you didn't all get applause doesn't mean that you didn't all do a great job. It just meant that the audience was confused, but not by your presentations, because those were all very clear. All right, so we're going to do Q&A from here in the room to begin. And if you're on the webcast, please type your questions into the text chat. Let's see. I can't see in the back of the room. Do we have a roving microphone? A handheld mic? We're supposed to. Do we have one?
We do not, I'm sorry.
We don't? Okay. Well, then I will repeat questions so that the webcast people can hear them. All right, so we'll start here. Make sure that you identify yourself, although in most cases I know who you are. Kala, you go first.
Okay. So Avi, I'm wondering with the brown dwarf, what is the major mass of the brown dwarf, and why would it be so much more dense than in general? What would account for that?
So can you repeat the question so that the webcast folks will hear it?
Yeah, the question was what was the mass?
Well, what's the major element in the brown dwarf that accounts for?
Oh, you mean what's the composition?
Yeah.
Okay, so the question was about the composition that makes the majority of the mass of the brown dwarf, and why is it so dense? The composition, I I am guess estimating that it is roughly the composition of stars, like hydrogen, most of it at least. The reason it is so dense is actually very well expected. This is the density that we expect from this kind of object. We expect an object at a mass of 40, 50, 60, 70 Jupiter mass to have the radius of more or less Jupiter, or maybe slightly smaller. And it goes to how matter behaves at this kind of environment.
So what is the radius of the brown dwarf again?
It is roughly 80% the radius of Jupiter.
Okay, thank you.
Okay, I think, Chris, did you have a question?
Yeah, Chris Praga, Science News. This question is for Melis. Do you know from our theories of rocky planet formation how it is unusual to see a planet with surfaces that has that much calcium carbonate?
Well, I think the real interesting thing is the carbon. So to get carbon to condense onto things, you need it to be in a solid form to make it really get in there. So theories of the formation of the solar system, you have this concept of the snow line. Things inside the snow line tend to be very dry because water is in a gaseous form. It doesn't incorporate into rocks very easily. It's sort of similar with CO2, except the CO2 ice line is much farther out. So you really don't expect things in the interplanetary system, or the asteroid belt even, to have large amounts of carbon because it's going to be in a gaseous form and the gas just doesn't incorporate easily. So yeah, that's why I said the question of where did the carbon come from is an interesting one, because either implies something very unusual about the formation location of this object, or it implies something unusual about how it was incorporated into the rocky object to begin with, or some combination thereof. If that matters for the presence of calcium carbonate so much, I don't know. I mean, I think if you have the carbon and you need a little water. So to make carbonates, you need water. And so if you have those conditions, it's going to form. That's not too crazy, I think. So the question for me really is, how did you get all that carbon there, and why did it just disappear at some point during the evolution cycle of the star?
I'd like to actually follow that up a little bit. We hear a lot about the possibilities of planetary migration during the evolution of planetary systems. And in this case, you've got a star that's become a white dwarf, so that means it's lost a lot of mass, so that even if there was no planetary migration during the earlier phase when the star was sun-like, presumably the fact that it became a red giant and blew off its outer layers and lost some mass would have affected the planetary orbits. Have you factored that into whether that might have played a role?
Right, so I briefly alluded to that by saying that if you had the carbon locked up as carbon dioxide, either in a solid form or a gaseous form, then the evolution of the star through the asymptotic giant phase. So during the asymptotic giant phase of stellar evolution, the star becomes several thousand to 10,000 times more luminous. What that basically means is everything in the planetary system gets cooked. And so regions where you can stably have water ice or CO2 ice now become unstable for those elements. Combine that with the fact that the star is losing mass at a high rate through a wind, means that any tenuous gas in an atmosphere or anything like that, it's going to be removed. It's basically being sandblasted by the star. So that's why our concern was if you want to have all this carbon in the form of CO2 ice or gas or whatever, it's probably just not going to make it if it's on the surface through the late end life of the star. So I hope that answered your question.
Okay, thank you. Any other questions here in the room? Do we have any on the webcast, Mike? No? Okay. Oh, new question.
Let me follow that up then. Nola right on the free answer. So isn't the star, when it's blasting off its material, doesn't it blast off carbon at some point? Or
Does the star itself eject carbon?
it's going through?
Yeah, so during the asymptotic giant phase, you can get various precipitates that form in the atmosphere of the star. Usually it's silicates. So there are a particular class of stars called carbon giants that do indeed have very unusual atmospheric chemistry. They have weird carbon stuff. It's usually because of dredge up. So that's a rare event, though. You don't normally get carbon giants. And whether or how much carbon is actually released during the final phases of stellar evolution, it's hard to say for a given one-off system. You can sort of maybe say it statistically. Whether that's important for this particular system, it's hard to know.
Okay, I actually have a question for Sean. When you were showing the animation of the planets transiting the star. It looked like both planets were transiting the star. Are you seeing the same effects? Are you seeing transits from both planets, and are they both moving around on the surface of the star, or against the surface of the star?
Yeah, we do see transits from both planets. However, only one planet is showing strong duration changes, so this effect of moving up and down the star. The other one is showing it much more weakly, and it's hard to observe by eye.
Yeah.
However, our models can pick up this small effect. And so it seems that both are perturbing each other as one would expect.
Okay. And then I also have a question for Jerry. I was struck by the alignment of the two stars in orbit around each other and the distant planet. And it just seems like it would be a really rare case to be able to get such an alignment. Have you looked at, for a system of that size, have you looked at how likely or unlikely it was that you found this system and that you might be able to find additional ones like it? Or is the reason that we haven't found these because you're just not going to get that alignment very often?
Yeah, so it's probably a combination of both. So whether these systems are common physically, then whether you see them aligned. And so the inclination of the outer orbit is 1/10 of 1 degree within being exactly edge on. And so that's a very, very fortuitous situation for us. And so if you just did random number statistics, there's probably, for every 50 to 75 of these types of systems that exist, you'll see, at most 1 or 2 in transit, from random orientations. And so we do have to account for that chance alignment when doing statistics of the populations, because it's much harder to observe the longer period systems in transit.
Okay. Nola, you have another question?
So my question is for Sean. So what was the orientation of the distant companion? You said everything else was in line. The distant companion, is it also?
We actually don't know that. The orbit of the distant stellar companion to Kepler 108 is not completely unconstrained, but it's not very well known. And so it's observed via adaptive octaves. So you can actually see on the sky 2 stars, but you don't know exactly what kind of arc the star is carving out, so you don't know exactly what type of orbit it has yet. So that's something that could be potentially observed with follow-up studies, although the period is very, very long. It's thousands of years, most likely, based on the separation between the 2 stars. So that's something that's hard to follow up immediately.
Okay. Sorry, I have a light right in my face. Anything online, Michael? Nothing? Okay, great. Then we'll wrap it up. So again, I'd like to thank Carl Melis from UCSD, Avi Shporer from JPL, Jerry Orosz from San Diego State, and Sean Mills from the University of Chicago. We have a briefing again this afternoon at 2:15 p.m., by which point we're hoping that we will have straightened out some of the technical problems we're having with our webcast. The subject is From Molecules to Galaxies. It'll be right here at 2:15 p.m. Pacific Daylight Time. So thank you all very much for your attendance, and we'll see you again this afternoon.